4.5 Limits at infinity. This section is mostly redundant. We have seen almost everything in previous classes or in previous sections. However, we will go over it now just to crystallize these concepts. So the goal is to find limits as x approaches positive or negative infinity, and tied to that is always the notion of horizontal asymptotes. So, first example, describe the end behavior using limits for the function given here. So we have seen that you can use the rule that when you have a polynomial over a polynomial, you compare the degrees, and if the degrees are the same, then you have to take the ratio of the leading coefficient. So here it's 3 over 1. And that means the limit as x approaches infinity is 3 over 1. Likewise, the limit as x approaches negative infinity is also 3 over 1. This is a graph of the function, but of course we didn't need that to answer the question, but it can help now see the kind of function that could have such an end behavior. In the following example, we see an example of where we have this kind of conflict of strengths between exponentials, polynomials, and logarithms. Here, the polynomial is actually a constant function, so it's even easier. You can just think in your head when x becomes greater and greater, the numerator remains at 3, whereas the denominator increases always, so the limit is going to be 0. What happens if we had the limit as x approached negative infinity? Then you would have to think this is 3, and y equals e to the x would approach 0 when x was going toward negative infinity. So the limit, if there was a negative here, would be negative infinity, or in AP Calculus AB, what we always write is dne. Okay. An example here of comparing strengths at the numerator and denominator. Both are polynomials, so this is when we look at the degree, and because the degree is higher at the numerator, we say it's top heavy. That means the numerator is going to win. This infinity is going to grow a lot bigger than that infinity when x increases, so the limit is positive infinity. And again, in AP Calc AB, you would just write dne. In this example, when we look at the range of sin x at the numerator, sin x always varies between -1 and 1. It's this wave, so the numerator is always somewhere between -1 and 1, whereas the denominator is going to increase and increase and increase. So if you imagine a huge value of x, then the numerator is somewhere between 1 and -1 divided by a huge number, so the limit is 0. The graph of this function would kind of oscillate between positive and negative, but become narrower and narrower as it approaches 0. This is a good example of a situation where a function can cross the asymptote. Some students think functions or graphs cannot cross the asymptote. It approaches without touching. Well, this function approaches y equals 0, and it keeps on crossing it. It just gets closer and closer as it crosses it over and over again. For part D, we're going to start by doing it on a separate sheet of paper, but please don't copy this because as we will figure out, it doesn't work. It's extremely rare that L'Hopital doesn't work, and it, I think, always works in AP Calculus AB, but this exercise was pulled from somewhere else. So, here the limit is the square root of x to the 4 minus 1 over x cubed minus 1, and if we try direct substitution, we get infinity over infinity, so it's an indeterminate form, and we can apply L'Hopital. Therefore, that limit is equal to the limit of the derivative of the numerator over the derivative of the denominator. A few things cancel out, x cubed and x squared, and then 1/2 times 4 equals 2, and then this part here, the negative, sends it at the denominator, and the 1/2 makes it a square root. So we end up with this expression here, which again is infinity over infinity. So we can apply L'Hopital again, and as we do that, we notice that there's kind of a mirror reaction to what we were doing earlier, and things cancel out, and this time the negative, which was at the denominator, sends it back at the numerator, and here we are. You might recognize that this is very similar to what we had at the beginning. We have the square root of x power 4, and then at the denominator we have a polynomial of degree 3. We can use L'Hopital again. I didn't write it here, and this is what we get. And when we simplify, we have this, so we could try L'Hopital again, since we are still in an indeterminate form, infinity over infinity, and so on and so on. Here we are, and once again, just like here, we have a square root of x power 4 divided by a cubic, and it seems like it's never gonna solve the problem. The only difference between this step and that step is that it multiplies by 1/3, just like here was multiplied by 1/3 from the original problem, with a little -1 that's different, but that's really not different enough to be significant. It looks like 2 steps further we would be at 27x³ at the denominator. So this denominator growing slowly might make us feel like, oh, okay, the limit is going to be 0, but there's actually another way to solve this problem, and this is what I want you to write on your paper. When you have a square root of a polynomial, you can actually say that this is similar in behavior to x², because the -1 here doesn't have a very big impact, especially when x is huge, like billions. The -1 is going to be very, very small. So the square root of x power 4 is almost x² in this case. And here again at the denominator, this -1 is negligible, so x³ -1 will very much behave like x³ itself. So it's approximately x² divided by approximately x³. And when we manage to change the expression like this, then we can see that for very large number values of x, this is going to approach 0. So this is what we would want to do in a situation like that. When you find the horizontal asymptote, it's a little bit like in the last example, question D. You want to kind of think of what happens when you plug in a very large number, x, either positive or negative, and see what the value approaches. So we are looking for horizontal asymptotes. That's the same notion as finding the limit as x approaches infinity or negative infinity. So when x approaches positive infinity for this expression, we have e to the negative infinity. You have to have the graph in mind, and you would see that this is going to get closer and closer to 0, and therefore we have 1 divided by almost 1, getting closer and closer to 1. So 1 over 1 is 1. On the other hand, when x approaches negative infinity, now e to the negative infinity is e to the positive infinity, so that grows without bounds, and we have 1 divided by 1 plus infinity, so that is going to be 0. The horizontal asymptote on the left is 0. So that function approaches a different value on the left and on the right. If I can trace with my cursor the graph, it does like this, then it goes up, and then it gets to the second asymptote.